Hello everybody. These notes are about parameterizing a curve, which means we have a Cartesian equation and we're going to go from a Cartesian equation to a parametric equation. That's what it means to parameterize. But before we do that, let's do these two experiments first because they're going to bring out a pattern. So go ahead, let's fill in t and x and y. Let's look at t on the interval from 0 to 4, 0, 1, 2, 3, 4. So go ahead, plot these parametric equations, figure out the x and y coordinates, what path does it make, and then this is a different set of xy parametric equations. This time t is on the interval from 0 to 2. So go ahead and try and evaluate them and plot them here. I'm going to pause the video, you try it yourself. Alright, so here we are. I've just plugged in the xy values, plotted and plotted. Check your own, make sure you have the direction arrows and make sure you've labeled time 0 and time 4. So the thing that I'm noticing is they seem like they're the same curve, maybe. Like certainly we have a point at 0, 0, at 1, 1, and at 4, 16, and that's the same as here, 0, 0, 1, 1, 4, 16. On this one, we've got these intermediate points at 2, 4, and 3, 9. And it's not totally obvious if this curve has those or not. So how could we decide if these were really the same curve? One thing that you might try is going from parametric to a Cartesian. So why don't you practice that one time here and here, just to check. I will pause the video. All right, so here we had that the x variable is just t. And the y variable is t squared. So I can substitute in, because x is just the same as t, I'll substitute x in for t, and y equals t squared has become y equals x squared. Let's make this t a little more like a t. What about this one? So here I've got x equals t squared. Here I've got y equals t to the fourth. T to the fourth is just t squared squared. So it seems like I can substitute x directly in here for the t squared, because I know that x is the same as t squared. So that gives me y equals x squared again. So by converting from parametric to Cartesian, I've seen that these really are the same curve. So what have we learned? One thing that we've learned is there is more than one set of parametric equations that can describe the same shape. So now's the piece that requires some insight. If I give you an x of t, could you figure out what the y of t has to be to make that same shape? So for example, let's say x of t is going to be t plus 1. What should my y of t have to be so that if I was going to eliminate the parameter, if I was going to go back to the Cartesian, it still describes that y equals x squared curve. Think about it for a minute. Okay, fair warning, I'm about to tell you. So what both of these sets of parametric equations have in common is that the y value is the x value squared. So if x was t, y is t squared. If x is t squared, y is t squared squared, or t to the fourth. And that makes sense because in the original Cartesian equation, like literally y is whatever x is squared. The only difference here is we're saying that x depends on something else. So whatever it is, however it is that you calculate x, you'd still want to square that in order to get y so that you're sure that you end up with that same relationship between x and y. So if x of t is t plus 1, the y value should be t plus 1 squared. Because that's the only way to be sure that for whatever your x value is, your y value is going to be the square of that. So this lets you generate as many different parameterizations as you want. What if x of t equals like 10 minus t cubed? What would y of t have to be to make that same y equals x squared? It's like whatever my x coordinate is, and this is the equation that tells me my x coordinate, I just have to square it. and that gives me my y coordinate. So it's like, this is like the heart of like algebra, like what it means to understand algebra. It's like, think about this expression as representing the x coordinate. And so here we're just saying, take that x coordinate and square it. As a conclusion, you might be wondering, well, hey, what's the point? Why, if all of these different things just describe x squared, what's the purpose in something very complex looking like this? Why would I possibly want this ugly thing when I could just have this one? X of t is t and y of t is t squared. And the answer is, look at the timing information. Here, this was time 0, 1, 2, 3, 4. So it looks like I'm getting faster and faster, but it takes 4 seconds to go that way. Here's time equals 0, 1, 2. So in the time it takes a dot moving along this path to get just to here, this one has gone all the way. So this parameterization is the same shape path, but the movement along the path is different. So given that, you might think, well, is it possible to start the point over here, have it move along the same path, but move in the opposite direction? How would you do that? Could we get it to move in other ways? And so that's where we're going to be headed.